Hello everyone, I'm Quentin Demoulin and today I will be presenting a new flexible photogrammetry instrumentation for estimating wing deformation in Airbus. So this work is part of the PhD I'm working on with Airbus in collaboration with the laboratory TESA, IRIT and the school ENP and SAIT. As part of the aircraft certification, wing deformation should be estimated in flight to evaluate and improve deformation models. So here we will present a new method to provide these measurements. In this presentation, we will have a look at the current reconstruction method applied in Airbus. Then we'll see the proposed photogrammetry approach with the photogrammetry principle, the algorithmic chain, and the new method called constraint bundle adjustment. And finally, we'll introduce the experimentations and results. So what is the current reconstruction method? The current method used in Airbus is the photogrammetry with single view reconstruction, where here we have cameras installed at the window position looking at targets stuck on the wing. To reconstruct the 3D position of the targets, strong hypotheses must be made, such as that the target motion are only along the z-axis and the cameras are fixed to the aircraft. Here we use retroreflective targets, which is really good to improve the accuracy and the detection. However, it requires flash illuminations, and therefore the synchronization with the cameras could be really a trouble during the test. Finally, here the targets are stuck on the wing, which is really intrusive and will impact the aerodynamic of the wing and therefore limit the flight domain of the aircraft. Then if you look at the picture here, you can see that we have only sections of targets which induce sparse measurements. And finally, the main constraints about this technique is that it's really long to install. It takes more than 1 week, because the camera must be installed rigidly to the aircraft, and strong calibration should be made using a laser tracker with a point-by-point calibration. Other methods were investigated with first the image pattern correlation technique, where 2 cameras will look at a pattern stuck on the wing surface to reconstruct its shape. And then you also have the reflectometry with the blade aircraft, where you will look at local deformations. Both of these methods are really intrusive and therefore difficult to use on aircrafts. So now, to deal with the main drawbacks of the previous method, we will introduce a new photogrammetry approach and start with the principle. Let's consider a set of 3D points capital X, which are observed by 3 cameras here. You will see on the image the observation of the points, and the objective of the photogrammetry will be to recover the 3D position of the points from the observation. And the first thing you will notice here is that each camera has its own coordinate system. So first of all, we will transfer the 3D position of the point from the aircraft coordinate system to the camera coordinate system. And to do so, we introduce a matrix P that will represent the rotations and translations of each camera. So now we will transfer, thanks to this matrix, the points from the aircraft coordinate system to the camera coordinate system. And then we will project the 3D points from the camera coordinate system to the 2D image using a new matrix K, which contains the camera intrinsic parameters, the focal, the sensor center, and the pixel size. This camera matrix K is known thanks to a calibration phase before flight. And as a consequence, we've got the 2D points xij, which is a function of the 3D points, and the camera matrices. However, we still have 2 unknowns here. So how can we recover the 3D position of the points from the 2D observations? There are several resolution possibilities. First of all, you can consider that the camera matrix P is known. That means that the camera are fixed during the test and will not move. Then you can also add constraints on the points themselves. So you can, for instance, say that you've got non-deformable solids. But for the moment, we will try to introduce no constraints at all. So we use a more generic method where we remove the aircraft coordinate system and work only into the camera coordinate system. And what we will do is we will estimate the matrices P and 3D point X that minimize the reprojection error. That means the distance between the estimated point projection and its observation on the image. So imagine that here you estimate the point x2 with some error. When you will project it onto the image, you will find that it's not the good point with respect to the observation, and here you will have a reprojection error, the distance between the estimated point and the observation, that we will try to minimize. This is called the bundle adjustment. Then some question can be raised. First of all, we are using a minimization process, so we need initialization. How can we get it? Second question will be, how can we find the observation xij, because everything is relying on it. And finally, we said that we removed the aircraft coordinate system, so in the end, how do we go back to this system? And to answer these questions, we will go through the algorithm of the method. The first step of the algorithm will be a calibration phase, which gives us the 3D position of the points and the cameras before flight. And this is done using many views of the wing from very different angles using a drone, and with a drone we save a lot of time. Then you've got the camera calibration, which gives us the intrinsic camera parameters kj using pictures of a chessboard. So to this point we've got our initialization of the minimization. The second question was how to find the observation xij. So first of all, we can use natural features of the wing, naturally present on the wing, to create these observations. So here we can use a suited algorithm that will find corresponding points from one view to the other by looking at their neighbor and properties. So just like here or here, for instance. Then we can go even further by exploiting the two black lanes that are naturally present on the wing surface. And to do so, we first need to rectify the images. So image rectification is the process that aligns corresponding points from one view to the other horizontally. So here, once you've got two lines here on unrectified images, when you rectify the images, the lines are aligned. And we apply this process on our wing views to align the corresponding points. Once the images are rectified, we can search for corresponding points of the black lanes by running through each line of the images. So here, if I go on this line and I find the black lane, on the other image I know that if I'm still on the same line here, the black lane is the corresponding point of the first one here, okay? Another approach will be to use markers plus graduation on the surface of the wing, and they will be really handy because the detection will be more easy and more accurate thanks to subpixel detection algorithm. So in the end here we've got our sets of observation depending on the condition and what we are allowed to put onto the wing. Then we can perform the bundle adjustment, and here for instance is a result of the reconstruction of graduation and markers inside the camera coordinate system. Which brings us back to our third question, how to transfer the points in the aircraft coordinate system. And to answer this question, we will add a final step, which will be the registration. This step, we will use an additional camera from the rear of the aircraft, which will be looking at the same points than the other cameras here, but also reference points that we will consider as undeformable during the flight, and therefore for which the 3D position into the aircraft coordinate system is known. So since we know the positions of these points, we can recover the position of the rear camera, and since this camera is also overlapping with the other views, we can use it to transfer all the 3D points and the cameras into the aircraft coordinate system. And finally, here you can see the overlapping of the reconstructed 3D point after registration with the 3D model of the wing on ground. So you can see that the registration phase is working. At this point, if we recap so far, we allowed any camera motions, marker motions, and we use no prior knowledge of the wing deformation. However, it is still possible to use prior knowledge about the aircraft mechanical limits to improve the wing reconstruction. And to better understand the idea, here are some examples. During the flight test, we know that the wing won't suffer any damage. So if in our reconstruction we see that at the first step we've got 2 points here with a distance L0, and at the second step we find another distance which is too big with respect to the first one, we know that it is not possible. Or same thing with the bending. We know that if we look at 3 points and at one step we've got a local bending which is too high, it is not possible because the wing has not suffered any damage. So we can think about many constraints, mechanical constraints like this, and create a set of mathematical constraints, GK, that we will introduce in our bundle adjustment here. Okay, so it will be the same minimization problem plus a constraint here. And to extract these limits, we will have a look at tests of ultimate loads. Ultimate loads are the greatest efforts that we can apply to a wing while it stays in one piece. The aircraft shapes under ultimate loads can be simulated using finite element method here, and then validated during static test on ground here. Then from these tests, we will extract 3D points of the wing for all possible ultimate loads. We will process them and create our set of constraints. Now let's have a look at the experimentations and results. First, we've prepared our system for flight tests. We selected 4 cameras with high resolution and a small size factor. These cameras will be placed at window position on top of the wing here, with 2 cameras looking at the beginning of the wing and 2 cameras at the end. And finally, we've got our camera here for the registration. Of course, we also have an acquisition computer that will trigger and record the camera videos. Then we designed a 3D support to install our cameras on fake windows here. So here we simply screw the camera on the windows, and then we selected meteorological windows that will be installed instead of normal windows of the aircraft to prevent any distortions. And finally, on the wing side, we will simply stuck a quadrant marker here of different sizes. So the goal here of our system is to have really an easy and non-intrusive installation. In view of the flight test, we've prepared a prior test on ground. So here we went on an A350-900 and we stuck our stickers here on the wing surface and markers on the lanes here. We installed 4 cameras here on the fuselage. We installed the cameras 1 meter above the window positions to simulate the views that we'll have in flight when the wing is bent. Then we performed a drone scan. So here we took a set of pictures of the wing to reconstruct the wing and get an initialization of the 3D position of the points and the cameras. Finally, here you can see all the views that we get from our cameras. Here the real view was provided thanks to the drone. And here you can see that we have already detected our lanes, our graduation and markers. So when we reconstruct, we've got here our set of points. Then we also went at the end of the wing and manually created a motion of the wing here, which were about 5 centimeters, and that we can clearly see here. And when we reconstruct, we've got this. So here you can see the 3D reconstruction of the motion with a magnification along the z-axis. And even so, it seems a bit noisy. You can clearly see a 5 centimeter motion, which is a lot lesser than what we'll have in flight. So this seems really good. Besides, introducing mechanical limits into our constraint model adjustment has greatly improved the results. As we can see in these graphs, here we've got the displacement of points during the motion sequence. On the left, you've got a point at the beginning of the wing, and here at the end of the wing. And in blue, you've got the reconstruction without constraint, and here in orange with the constraints. And what you can see clearly is that without the constraints, it's a lot more noisy. And here, especially, you can see that with the constraints, you've got a good sinus, which is of about 5 centimeter amplitude, which corresponds to the motion we introduced at the end of the wing. We can also see that using the mechanical limits here will improve the stability of our points by removing outliers. So in this graph, what you can see here is the reconstruction of the points at the beginning in the blue cross on the background, and on the top, the points represent the reconstruction at the end of the motion sequence. So here, without constraints, you can see that many points are moving during the sequence, and you've got a lot of outliers. And here, with the constraints, all the points are staying on their positions within the mechanical limits. After all, using the mechanical limits improves the robustness and the stability of the method. In conclusion, we've proposed here a new photogrammetry method that is easier to install because we use camera screwed directly on the windows, plus marker stuck easily on the wing surface. It is more flexible because camera can move, and we allowed more degree of freedom of the 3D point on the wing. Then we can also provide dynamic measurement thanks to the use of video cameras. We have a full mapping of the wing because we can easily detect points all along the wing. And we do not require any dedicated tests because our devices doesn't have any impact on the aerodynamics of the wing. In the next steps, we'll have to evaluate the method in flight with contour measurements, and we will assess the metrological accuracy of the reconstructions. Thank you for your attention, and if you have any questions, feel free to ask.